Hi everyone, I am Rafi Rashid. Today I'll present our work on gradient-free privacy leakage in federated language models through selective by tampering. The central question is pretty simple. Can one federated learning client recover another client's sensitive text without ever seeing that client's gradients? Federated learning is often presented as a privacy-preserving alternative to centralized training because raw data remains on each user's device. In federated averaging or average, in short, clients share updated model weights rather than for example, gradients. However, keeping raw text local does not necessarily prevent the model from memorizing the text. Most previous privacy leakage attacks assume a relatively strong adversary, for example, a malicious server, direct gradient access, changes to the model architecture, or some form of side channel observation. To study a tighter and more practical threat model, our attacker is simply another federated learning participant. It observes the same intermediate global model snapshots available to other ordinary clients, and it tries to extract sensitive text belonging to other participants. Our attack begins with two key observations. First, privacy-sensitive text produces a distinctive footprint inside a language model. When GPT-2 is fine-tuned on regular English sentences, the resulting weight changes are distributed relatively evenly across the transformer blocks. But when the training data contains out-of-distribution sequences, such as phone numbers, credit card numbers, or login credentials, or physical traces, the largest changes become concentrated in the MLP sublayers of the final transformer blocks. We refer to these selected layers as cluster, and we treat them as potential memory hotspots. Our second observation is that the privacy signal is often strongest before federated training ends. When a victim participates in a training round, the exposure of that victim's private sequence increases. In subsequent rounds, averaging and updates from other clients gradually weaken the signal. Therefore, an intermediate snapshot can leak more information than the final converged model. These two observations motivate our attack. First, identify like victim rounds, and second, selectively amplify memorization within Ulster. In our third model, the attacker is an ordinary malicious federated learning client. The victim is another client whose local data contains templated sensitive text. For example, the phrase your verification code is followed by a secret value. The attacker needs to know the non-sensitive template or prefix but does not know the secret suffix it is trying to recover. The attack pipeline contains four stages. First, the attacker stores the global model snapshots it receives. Second, victim round identification or VRI estimates which snapshots were influenced by clients containing sensitive or out of distribution things. Third, maximizing data memorization or MDM, which modifies only the selected weights in L-star. Finally, the attacker performs either prompt-based data reconstruction or sentence-level membership inference. We study a static mode in which snapshots are transformed after training and a dynamic mode in which an amplified victim signal is injected into the attacker's local update during training. First, the victim round identification. The victim round identification uses only patterns in the model's weight chains. The attacker first creates two reference models. The first, G sub R, is fine-tuned only on regular English text. The second, G sub S, is fine-tuned on regular English combined with attacker-generated dummy-sensitive sequences. Importantly, these dummy sequences do not overlap with the victim's private data. They produce only the general out-of-distribution sequence structure or sensitive information. For every observed global snapshot, the attacker computes a change vector using only the selected layers. It then compares the vector with the regular and sensitive reference vectors using two pairwise t-tests. A snapshot is labeled as a victim snapshot when it is statistically different from the regular reference, but statistically similar to the sensitive reference. Across experiments involving 1 to 10 victims, VR achieves approximately 86 to 94% recall and 77 to 82% precision. This shows that useful intermediate snapshots can be identified with substantial accuracy even without assistance from the server. Now, the maximizing data memorization section. Once a victim snapshot has been identified, we amplify its memorization using one of those two methods. The first method is selective weight optimization, or SWO. In short, SWO measures the difference between the victim snapshot and a regular reference model. It then increases the magnitude of that difference while preserving its original direction. Conceptually, SWO strengthens an existing sensitive data signal rather than moving the model weights in an arbitrary direction. The second method is called Weights Transformation Learning, or WTL in short. Here, the attacker creates a supervised transformation using only its own regular data dummy out of distribution sequences. This learned mapping captures how selected weights typically change when a model moves from regular text behavior towards sensitive data behavior. The attacker then applies this learned transformation to L star in the identified victim snapshot. Both methods strengthen the late layer memorization signal. However, WTL follows the characteristic sensitive data transformation pattern more closely and consistently performed better in our experiments. Most importantly, neither SWO nor WTL requires access to gradients computed from the victim's data. Now the experiment setup, we evaluate the attack across model families. There's four model families actually: Gamma, 2 billion, GPT-2, BARD, and a compact Llama 2 studies there. Our datasets include paint tree bank and whitetext 103 augmented with 200 unique synthetic canaries. We also evaluate naturally occurring sensitive information using 125 private sequences identified in the ingrown email corpus. The main federated learning setup contains 100 clients. 20 clients are selected in each round, and training continues for 700 rounds with 5 local evokes per round. For model above 1 billion parameters, we use parameter efficient fine-tuning with QLoRa, and we evaluate successful data reconstruction, exposure, membership inference, recall, and precision and validation perplexity, allowing us to measure both privacy leakage and model utility. So here are the main results. The results show that substantial private information can be recovered under this client-side trait model. Our strongest configuration reconstruct 142 out of 200 canaries, corresponding to a reconstruction rate of 71%. On the real enrolled dataset, the attack reconstructs 80 out of 125, which is around 64%. For membership inference, the best dynamic plus configuration the dynamic plus configuration reaches 61% recall. Here, the plus sign means the server provides passive assistance, for example, by identifying victim rounds, but does not actively poison the model. The progression from static to dynamic plus demonstrates that the client-only attacks are already effective, while passive server cooperation provides an additional improvement. We also compare our method against Decepticons, which assumes a stronger adversary and actively malicious server that manipulates model parameter. Our results are comparable to Decepticons on GPT-2. On BARD, however, our approach reconstructs approximately 2.6 times as many canaries. Overall, these results show that exploiting intermediate snapshots and selectively modifying a small portion of the model can substantially strengthen both data reconstruction and membership inference without accessing victim gradients. We also discuss some privacy defenses. We evaluate several potential defenses, actually. The main conclusion is that no single defense is sufficient. Differential privacy reduces the number of successful reconstruction. However, stronger privacy settings noticeably reduce model utility as indicated by increasing validation perplexity. Secure aggregation or homomorphic encryption can prevent the server from observing individual client updates, but these approaches provide limited protection against our core client-only attack because ordinary clients still receive the global model. The most practical defense is therefore a combination of techniques. First, scrub predictable personally identifiable information before training. Second, duplicate repeated records. Third, apply modest edge depend regularization, which suppresses privacy-sensitive neurons without producing the severe utility loss associated with hard tuning. On the Enron dataset, combining AdDepen with scrubbing reduces successful reconstruction from 67 to 29, while retaining substantially better utility than an aggressive differential privacy configuration. Therefore, we recommend a balanced defense stack combining data cleaning, deduplication, and modest regularization rather than relying on a single mechanism. So the takeaways. To conclude, there are three main takeaways. First, intermediate federated learning snapshot can leak more private information than the final clean model. Second, weight patterns in the final transformer layers can reveal victim rounds and can be selectively amplified to increase memorization. Third, meaningful client-side privacy leakage is possible without victim gradients or active control over the server. Our experiments focus primarily on medium-scale English transformer models. Extending these analyses to larger multilingual or multimodal and fully encrypted federated learning settings remain an important future work. Thank you for everyone's attention. The source code is available through this QR code shown to this slide, and I'm happy to take any questions.